this is conservation of energy, and this is what you have to understand really to get a score on the next test that is above room temperature, okay, in Fahrenheit, okay? So the idea of conservation of energy is the notion that energy is neither created nor destroyed, it just moves around. You already have that in your notes, right? I could also write it another way, right? I could say the total energy of a closed system remains constant, okay? And for this, I've got a nice little demonstration here. Let me just make it wide. Oh, very wide, okay? And I've got a bowling ball here. And this is going to be our closed system. And when we say a closed system, we mean that the... Can I be seen in here? Am I on the camera? No, I'm certainly not. Somebody want to pan that thing toward me a little bit so we can see that on there? Okay. There we go. There you go. There you go. Okay. So this is my closed system. And when we say the total energy of the closed system remains constant, that's like, what does that really mean? Well, let's suppose that we say this is zero potential energy. We can do stuff like that. Okay. So this is zero potential energy, and it's not moving, even though it really is moving like 900 miles an hour that way. Right? Let's just say it's moving. Okay, relative to us, it's not, right? And if I do work on this thing, I'm transferring energy to the system, yeah? So let's suppose that I do 10 joules of work on this, yeah? Okay? If I let it go, well, at first, what kind of energy did it have to begin with? It had potential energy. In fact, if you wanted to figure out the amount of work I did, that'd be about the only way you could do it. You would have to go, if you look at it, didn't it change its height? Yeah? It would be very hard to do force times distance because the force is ever changing. At the beginning, it's not very much. In the middle, it's more. And at the end, it's actually somewhat difficult to push on it, yeah? It's like a spring, only it's probably not F equals kx. It's some like sine of something, yes? Okay? So to figure out the work done, you'd have to actually do mgh, know the mass, know the change in height, multiply by g, yeah? Okay? Now, let's suppose that all, when we work it out, is 10 joules. When I let it go, it swings, and at the bottom it has, freeze frame, zero potential energy, so it must have 10 joules of kinetic energy. Well, you guys are good. There we go, right? Now let's watch it again. There it goes, right? And swings back and forth. It's got potential, kinetic, potential. If I stop it here where it's got 8 joules of potential, it's got 2 joules of kinetic. It always adds up to 10. Yeah, there we go. We're not making fun of people, are we? Okay, there we go. Now if I stop it here and it's got 1 joule of potential, it's got 9 of kinetic. It's going pretty fast, but not as fast as it's going to go when it's all the way at the bottom, yeah? So when it's at the very bottom, at that instant, it's going the fastest that it's going to go. And when it's at the top at either side, it's got a 0 velocity, because if it's not 0, there's no at the top kind of a thing, yeah? Same thing, right? Okay? Isn't that wonderful? That's a wonderful thing. Okay? Now, the second thing, and this is the equation right here, okay, is that the total energy before equals the total energy after. And we're going to construct this thing in a lot of ways, but this is one way to do it. So basically, these things are word problems, and you're going to look for a before situation and an after situation. There'll be a bicyclist going up a hill. At the bottom of the hill is before. At the top of the hill is going to be after, or something like that, right? So total energy equals total energy after. Now, how do you add up the total energy? Well, these are the ways we can know energy. Work can be force times distance. Okay? We can have E potential energy is m times g times h, right? We can have that the kinetic energy is 1/2 mv squared, right? And then we can, now, you know, this is an exciting development today. We could also have a spring that's sort of coiled up or something like that, right? So we could have the potential energy of the spring is 1/2 kx squared. And it, by the way, is my goal to have a problem where there's a spring that's compressed, but the thing's already moving. It's at the top of a hill, and we push on it, and all of those things are where the energy comes from. Wouldn't that be amazing? That's like the Holy Grail. When I write that problem, okay, I will see this sort of shining golden cup, maybe above your castle or something. I'd be like, right? But it'll just be the Grail beacon, right, or something like that. Okay. Anyway, So this is our goal. This is how we set up our total energy before. Sometimes people are very financially oriented. So sometimes people like to think of assets, right, equals expenditures. This assumes that we don't have like a reserve fund or something like that, right? You know, it could be expenditures plus reserve or something like that, but right. Sometimes it helps to think of it in terms of comes from, right, equals goes to. And then there's another tricky little bit, but before we do that, okay, we have to deal with the possible death of your instructor, okay? Because I believe in this so much that I'm willing to put my life on the line. Now, before we go there, we've got to go someplace else, far darker than that, okay? Let's suppose that you have an assailant, and you know you must kill this assailant, okay? Instantly with one blow, possibly without any suffering, right? Where do you hit them and how?
Jugular.
Jugular. No, that's not what I'm looking for. Might work. Not looking for that. Right between, what do we do? How do you, where is it? What's the death blow? Temple. No, come on. Somebody knows it. What is it? Where do you hit them? Come on. I know somebody's sitting on this one.
Right in between.
Somebody's a killer.
Right in the nuts. Nose.
The nose! Chris is up here. He's like this calm, kind of mellow kid, right? Okay? But hidden deep down, right? He's got the ability. How does it work? What's the blow and how does it work? It's like the palm of the hand. It's like this, right? And you just, there it is. Yeah, Jacob's got it too. He's like, I'm ready to go, you know? Okay? And he's not going to use it, right? It's like living in Arizona. Everybody's got a handgun. This doesn't mean they're going to use it, right? Okay? Right? They could use it though. Okay? So just think about this, right? And how does it work? There's like these bones that are like these swords of Damocles dangling above your brain, right? Okay, there they are, and when struck properly, the nose, those things break off along their like perforated, those like pre-perforated little things there. They break off, and the butt of your hand jams them back into your brain, just like that. Yeah, there it is, right? I'm sure this is, by the way, not exactly true, you know, but certainly if the butt of your hand could do that, right? I'm pretty sure that a bowling ball named Artie, okay, is definitely going to rearrange something, okay? So what I'm going to do is I'm going to put my head against this wall so I can't back out of the whole thing, right? If energy is not conserved, I'm going to put it right up against my nose, and if energy is not conserved, it can swing and possibly come higher, right? Or it could, by the way, be lower. So it's kind of a 50-50 thing, right? You know, death, not death, right? You know, but I'm willing to put my life on the line there, okay? Now, if I do die, just understand that it was painless. I will just sort of fall in a little heap here, a broken heap, right? Just press, there's a little button right here. Press that button. Deb Olson will come on and say, yes, and you just say, well, we need a substitute for the rest of the period, okay? Murray, energy was not conserved, and Murray died, you know, okay? Some people wouldn't take this risk for you, but I'm, you know, okay. And so I'm actually pressing this right into my nose, into the soft tissue of the nose, so that if it does come back a little higher, it's going to hit the sort of harder stuff that's in there, right? It's a long nose, you know, you got to... Okay, here we go. Now, did I talk about how you release it? Yeah. You want to just sort of let go of it, right? Because if you push it, right? If you push it, it comes up higher, right? And the reason it comes up higher is that it's now got the potential that it had plus the force times the distance that you gave it, right? So when it comes back up and doesn't have, right, it's got to come higher. Does that make sense? Does everybody understand that? Okay, good. Thank you. A little applause. All right. Okay. Now, if you're going to solve these problems, what? Oh, I didn't actually do the thing. It's like Bilbo. He didn't actually leave the ring behind, right? Yeah. Okay. Obscure Tolkien reference. Okay. Here we go. I'm not afraid of the big bowling ball. Yeah.